I'm Pamela Hughes, Senior Director of Philanthropic Engagement here at IAS. I think I know every one of you in this room, and I am delighted to welcome you as we kick off our Friends Lunch with a Member talks. I don't think we did them last year, but I'm really glad that we're back and to see all of you. Our speaker today is Sihao Cheng, postdoctoral member in the School of Natural Sciences. Sihao received a BS in astronomy from Peking University in 2016 and went on to Johns Hopkins University to earn both an MA and PhD in astrophysics. He did a one-year postdoc at Johns Hopkins while also a visiting fellow at École Normale Supérieure in Paris. In addition to his current membership at IAS, Sihao is a visiting fellow at Perimeter Institute in Waterloo, Ontario. His research is focused on using statistical analysis to reveal beautiful, his word, physics and make discoveries. Sihao's interests range from observational cosmology to galactic dynamics, stellar physics, and planets. His work has led to cosmological applications of a new statistic that borrows ideas from deep learning, a discovery of freezing stars that shine out of gravitational sedimentation, and a Jupiter candidate that opens a unique window to study exoplanets around massive stars. Sihao is also working on a new method to map stellar orbit distribution in the Milky Way and the search for Planet X, a hypothesized new planet in our solar system. Fun fact, in high school, Sihao and his twin brother found an efficient way to take spectra of meteors with a digital camera, designing a prism device that can screw into the front of a lens. I understand these devices have since been manufactured and can now be purchased. In addition to physics, Sihao's interests include math, philosophy, classical music. Naturally, he plays 3 instruments, as well as kendo and anime. So now please join me in welcoming Sihao Cheng. He is happy to take questions during his talk, and we will also have time for discussion afterward. Sihao.
Thank you very much. It's my pleasure to be here giving this talk. I want to say that I have questions. I was hesitating about whether to talk about the Planet X search or this work, but then I realized that's, I mean, still ongoing work. Let's see if I really find Planet X in our solar system, I will probably give another talk next year. Right. So today I want to talk about a work. It's actually a distraction from my own field. I mean, astrophysics. It's more about the statistical side. I mean, related to machine learning and computer vision, something like that. But also we try to apply it to astrophysics. So it's about a mathematical vocabulary that can describe textures or patterns or the like morphological structures in physical fields. And we try to make connection between these tools, statistical, pure mathematical tool, and physics. So according to the great scientist Gibbs, doing theoretical science is very much about finding a viewpoint from which the complex world around us looks simple. So nowadays we have, I mean, our world of the human being actually is a very, I mean, filled with data, and these data are usually in array form, right? We have pixels of images, we have like time series of data, where we can have data cube, like simulations of the atmosphere, of clouds, of ocean. So to get information from these data sets, we really need, I mean, a quantitative vocabulary to compress these high dimension thing into something we can really communicate. So that's the basic idea of this work. And when we talk about these vocabulary, right, if you ask a scientist, what is the most popular one, that will be the so-called power spectrum or a variance analysis. You measure the variance of your signal at different scales. That's basically the baseline. But actually, unfortunately, it turned out to be very difficult to go one step beyond these variance analysis due to various reasons. I just want to emphasize this. I always remind my cosmology colleagues when I give this talk that once you have this vocabulary, because they are too much obsessed to quantitative analysis, but I would argue that once you have this vocabulary, it can do much more things than just fitting cosmological parameter to 1%. Because a lot of science is done with sometimes no model at all, right? We are exploring a new field. So there we basically need data exploration. And you have this vocabulary that can help you when you see the data, right? You can help you to describe and try to think, organize the thinking. And also when you have some coarse discrete model, these vocabulary can also help to do classification. And also at last, if a field of physics is very mature, you already have a parameterized model, quantitative model. You can also use this statistical quantity basically to do parameter inference. So I want to start with this beautiful visualization to give you a sense of why it's difficult and why it's interesting to describe these patterns. So these two fields look very different, but actually if you measure the variance or the power spectrum, they are the same. So this no one for a long time probably, I mean, not really long. So surprisingly, not really long. This is no one probably 50 or 70 years ago. So it's really surprised that before that people didn't realize this. But also you see it's quite obvious. So this morphological pattern is related to these coherent structures, and you see the fluctuations are concentrated at some particular region, more limited region, then widely spread into the whole field randomly. So in some sense, you have a lower entropy of the left panel, and the right panel, which is a so-called Gaussian random field. That's very different. That's a high entropy thing, right? So the question here is, how do you quantify the difference between them? We can all tell the difference, but do you have a mathematics for it? Oh, the screen. It looked much better on my screen. But fine. So another example of these morphological, I mean, yeah, so the question I always get is this sounds like doing science by eye, right? It doesn't sound so nice for scientists. But I still feel very um inspired by just looking at these patterns. And because when you see the difference, you know that there must be some physics inside, right? So here is two fluid simulations, one with magnetic field on the right and the other without magnetic field on the left. And magnetic field basically changes how these fluid, I mean, elements interact with each other, how sticky it is in a anisotropic way. And they look different. Their power spectrum again is quite similar. So then can we quantify the difference here? Yeah. So when I mean, we just got, the Nobel Prize of this year is just released, right? And in physics and in chemistry, both of them are related to AI. So you might also think, okay, we have AI now, and why can't we just directly use AI to do this? And that's a very natural thing, and it's a very good idea. And actually, the statistic I talk about is borrowing some ideas from AI, but it's a simplified version. Right. So the point I want to make is that you see on the left there's a variety of different images. You have something at the top is called Gaussian random field. Actually, the cosmic microwave background in our universe is very well described by these Gaussian model. But you can increase complexity, go to some physical fields with these structures, and then go to like even more complicated, like real world objects. So I would argue that just by looking at this, you see the complexity of the physical field seem to be in between of the simple model and very complex world. So maybe we don't need like millions of words in our vocabulary, which is stored in the neural network, right, to describe these things. Probably we can just use a much smaller vocabulary, which is already able to describe the physical structures. So that's basically the idea of these statistic. And by the way, actually, so this is not invented by me. This is invented 10 years ago by computer vision scientists. But I did a lot of development and also interpretation of these statistics. So it was developed under the motivation to basically understand how the convolutional neural networks is working, how to organize basically these morphological information. So that's another aspect. You can view it as a simplified neural network to apply it to physics, which is simpler to use. And also you can use it as a viewpoint to understand neural networks. Richard Feynman once said that if I can't create anything, I don't really understand it. So here I'm borrowing the same philosophy to basically try to build a generative model with this statistic to show you like what is really inside this statistic, what is in the eye of this statistic, like the world look like. So the left one is a real science like field that's called the gravitational lensing field. It's basically a projected version of matter distribution in our universe. So there are clumps in our universe. And if you want to do a generative model, like basically I want to create a field look similar to this, and the tool I can use, let's say, is some statistic. So if you use the so-called power spectrum alone, where you require the variance statistic to be the same as these real world field, but you don't know any other knowledge, then you basically get these blob, like random widely spread structures, which look differently. That's basically the Gaussian field. If you use a traditional other statistic, you get slightly better, but still very different. So if you use these final new statistic, I hope the visualization here is okay. You see that it looks very similar to the left panel, the real panel. So this basically means I can use this statistic, which is a very finite, limited set of words, to build the whole field with like a lot of pixels. So the distribution of that somehow is well described by these like limited number of words, I mean mathematical words. And how do you understand? I mean, how to understand this? Another analogy is, as you know, now like AI, there's a also generative model, right? There's a fake face generation. And here I'm showing the example. This is the early version, like probably 5 years or 10 years ago, how AI can do in the job of generating human face. So it's like basically a failure, right? We think that's far from truth. But this is nowadays like what the most advanced AI can do. So it's a similar idea, like the improvement of these generative model basically means something, means you really understand the original image. Yeah, so finally, I mean, here is a similar idea. The left is a real physical simulation. The left is a generative, generative model based on the statistics. So just want to say one word, like in fluid dynamics, this has been very difficult to do. It's only after these new statistics, people can really generate, something with pattern really look like a fluid field. Before that, it looked very differently. I feel I might go over time. Let's see what time is it now. It's already 30. Um, yeah, let me skip this first. This is just want to say that, the design of this statistic is related to neural networks. Is some simplified version of it. But I want to go further to this slide first. This is a way we try to not only generate the fields, but do more quantitative science, which is to try to interpret the meaning of these statistics with the technology of a generative model. So here the idea is, so originally, right, at the first task, I have an example image and I try to generate new images similar to that. But now I say, what about I tell you that I want this statistic to be high, the other to be low, and see what's the effect in the image so that I understand, right? If this one statistic is high, if I see curvy pattern, I know this means the curviness of the structure. If I see the other is high, another is low, I have a particular pattern shown in the image, I know that I can do the correspondence of the meaning, visual meaning, and the value of the statistic. So that's basically what I'm trying to do here. The left panel is basically one number. If it's high, you see you start to have sparse like structures. If it's low, the structures are more widely distributed. And the right panel is another meaning we found. It's a combination of the statistic. But when that number is low, you start to see curvy structures. And when that number is high, the curvy things become straight. So it's really a continuous transition. So here I'm showing one like small tool to visualize this. I hope it's yeah. So this is the number basically. As you see, when it goes to large, you start to make the structure straight, and you can really do this in a continuous manner. I think probably this is also the first time people do this. There are similar analogy also in neural networks. People try to understand what is one neuron really remembering, what is the meaning of one neuron, and the way they do it is the same. So they go back to the neuron and they let that neuron to be very high, and then go back to the image and see what's in the image, how the image look like when this neuron is extremely high. And you might have known, I mean, online saw some pictures of that, right? That's the deep dream like of neural networks. Some very deep neurons actually mean very high level concepts in the image space. Like some neuron remembers dog face, some neuron remembers like cat face or the leg of something. So this is basically a shallow version of that because the structure, like in physical fields, usually is not so high level. Um, yeah, so I hope that visualization interpretation look inspiring. Um, Yeah, so now I'm going to do some more scientific applications. One idea we have is to look at the ocean pattern. So this is like the temperature map of the ocean of the Earth, right? So there's a NASA, I think there are two or more NASA satellites taking infrared photos of the Earth's surface every day on the sky. And then you can have basically a map of the ocean temperature. And if you zoom in and get like small cutouts of 100 by 100 kilometers, you basically get all of these like panels, images. You see that they are morphologically very different. So this is already organized by the statistic, right? So I just measure the sparsity in the x-axis and the curviness in the y-axis, as I showed before. And you see that these data set can be organized in some very regular manner. So for example, if you go to the corner of this distribution, that's usually where the outliers or some interesting thing happens, right? If you go to the corner and say, what about I want a very, very high curvature. I mean, by the way, up is straight, right? Down is curvy. Um, so um, so the interesting thing is really if you go to that value and query like cutouts with this low number of these statistics, you do see all the images show like curvy structures, and they have actually interesting spatial distribution pattern. So these are basically swirls in the ocean. And similar thing, you can try to organize the morphology of galaxies. This is another a difficult question for a long time for galaxy astronomy. Right. So another example we try to do, which is actually the main focus in science, is to try to apply it to cosmology and better measure the matter distribution in our universe. So idea here is that the distribution of matter in our universe is not uniform. We know that, right? We have people here, we have table here, and they're also air. They are not uniform. And also, if you go to larger scales, the Earth is very dense, and then it's almost empty between the Earth and the sun. And if you go to even larger scale, like between stars and stars, is almost nothing. And between galaxy is almost nothing. It's only when you go to very, very large scale, the universe seem to become more uniform. Right, so these clumpiness actually can tell us about the evolution history, like how fast the universe expand. It can also tells us like the initial condition of the universe. Of course, if it initially is very clumpy, then now it's more clumpy. If it's initially flat, it's more flat now. I'm not sure I want to go to the details of this. I mean, one way to measure basically to map where there are more matter in our universe, where's less mass. I mean, because majority of the matter in our universe is dark matter, so they don't really emit light. So how do do that? How do you map them? And very fortunately, there's a gravitational lensing effect. So how do you understand that? That's very similar to when you look down the like a swimming pool. So there are wiggles, there are waves on the surface of the water, right? If the water is very like clear and clean, you don't really see directly the surface of the water. But by the distortion of the grid pattern in the bottom of the swimming pool, you can like derive, you can infer that really there's a wiggle in the surface of the water. So it's a very similar idea. We look at like very far so-called background galaxies, and their shape are slightly distorted, actually just by 1%. But by statistically measure that, you can do it quite well. And by the distortion of background galaxies, you can try to infer the amount of matter or map the matter in the foreground. So that's the gravitational lensing idea. And this is actually like one major part of modern cosmology nowadays. Yeah, so this is basically the matter distribution for different cosmology. And again, the reason I want to show this is analogy of the first image I show, which is the filamentary structures in the left and Gaussian blob in the right. So here is a weaker version. They look more or less similar, but if you see more carefully, you start to see that, okay, it seems qualitatively different. The left probably have more small blobs or like more peaks. The right probably is more uniform, like fewer large peaks. And that's true. Indeed, there is a difference. I just want to show you how difficult it is even for human eye. And so the task here is we want to use some quantitative statistical tool to really measure this difference. To make the story short, there's a traditional way of using variance analysis, which give you a constraining power low. And there are different other ways to do it. And also people try neural networks. And here the plot is basically telling you that the performance of these new statistics is the same as neural networks. So I think this is really encouraging. And also this is confirming my philosophy I said in the beginning, which is physical fields probably is not as complex as the biological world. So maybe there's no need here to use neural networks. I hope this is not too technical. And again, the visualization here is not as ideal. I mean, there are some, okay, fine. This is real data. Okay, so what I showed before here is simulations. And I just want to show you that we apply it to real data. This is one of the best measurement we have of the universe matter distribution. And in very near future, there's a Rubin Observatory, which is in construction now. I think it will start to work next year in Chile, and the United States is investing a lot. I think that's probably listed one of the major scientific projects from the Congress. Right. So the point here is this is what we have now, and in very near future we will have much larger mapping of the universe. So this is what we have now, and this is what we will have in like 3 to 5 years. I mean, it takes time to observe, right? Of course. Right. So this can be a very relevant thing very soon. Right. So the improvement we can get from these statistics basically 2 times better in the amount of matter in the universe. Yeah, so I hope this is not too technical, but that's what the cosmologists are doing, try to measure amount of matter and clumpiness of the universe. Um, and hopefully that can tell us about some like new physics of right. So finally, let me see how much time I have. It's almost 30 minutes. I only have a little more to show visually. I'm not sure what I can describe with word. This is basically just more visualizations. We try to build enhanced version of these statistic, which can perform better, basically. So this is example. The left is real thing, physical thing. The middle is the reconstruction with old version statistic, and the left is with new version of statistic, just to show you that there is a step. I mean, we didn't get the final the good performance just one step. It takes some time for us to think and to improve. And also other fancy things visually. Again, you have one texture in the left, you have one texture in the right. You can use this statistic to do interpolation, to have a gradual change from one type of features to another type. And this is not trivial, by the way, right? It's only when you are able to quantify something, it becomes trivial to do interpolation, right? If it's a region like patterns, like I have a cat, I have a dog, how do you do the intermediate thing? Like what is in between of a cat and dog, right? It's not so obvious. So that's basically why it's important to have this vocabulary. And this again, some other interpolation. Um, we try to make sense of this statistic. This vocabulary, by the way, is becoming very large. It's several thousands now. So we try to further compress it and get like some meaningful subsets of it. Yeah, but it's just by looking at it, I feel it's very enjoyable. That's because they are just purely generated from some numbers. They're not some artist like doing painting. This is some art by computer and pure numbers. Um, yeah, so again, just visual things. Yeah, so finally, I want to come back to the point of a vocabulary and words. So you might wonder when we talk about a language, the first thing is how many words are there in this language, right? And I can tell you now it's about 10,000 as shown here. Um, but I mean, that's not bad, but it still sounds a lot. So the good news I can tell you is that actually to describe this field, like one particular structure, you don't need to use the whole vocabulary as in daily life, right? We don't need to use all the words to describe just one thing. So the number of words now we can do to describe these fields is actually several hundred. So for example, to describe this, you probably need 200 numbers. Um, I'm not sure whether we can do better, but I think it's already an encouraging step forward from the 10,000s. And if you really think about it, it makes sense, right? Because the world, the variety of spatial structure is actually huge. It's not like linear, right? You just have a few possible things. You can imagine like many different patterns that look slightly different, but actually not the same. So if you just use like 100 words to describe it, I think it's already a good deal. Okay, so that's what I want to show today. To summarize, I think there's a variety of complexity. There's a gradient of complexity in our world, and somehow many physical fields, their entropy is kind of in between. So the question is how to extract information from these type of field. Of course, our tool need to fit the property of this field. And I did some development of the so-called scattering transform statistic. It's in between in many ways of this very simple statistic and the neural networks in terms of like both the complexity, the number of statistics you need to use, and also the design, the definition, also borrow ideas from convolutional neural nets. And they show a lot of visualizations with a generative model. Hopefully you enjoy it. And also I showed that in the cosmology application, its performance is very similar to convolutional neural nets. I hope this is enjoyable and yeah, help you probably better understand the world of computer vision and also machine learning nowadays. Thank you. Yes.
If you look at different parts of the universe, look out that way, then look out that way, does it look the same?
It depends on the scale. So if you thought that they're talking about very large patches, statistically they look similar, right? But if like you look at exactly the position of the sun and exactly the position of the Earth, they are different.
So the answer is yes.
Yes, at large scale.
Can you use this to estimate the amount of matter in the universe? Can you use these formulas to estimate how much matter there is in the universe?
Yeah, that's very good question. It's actually also a very technical question. To measure the amount of matter, you can think about many ways. This most straightforward way is to just get one volume and measure the mass there, and then measure the volume of the universe and multiply it by the density, right? But somehow that's not how cosmologists do measure these nowadays. The reason is very difficult actually to calibrate the amount of matter in one volume, especially when they don't emit light, because the majority of the matter now, I mean, is in dark matter form. So then cosmology nowadays, they adapt another way to do it, which is to use structural fluctuation and the matter's influence on the expansion of universe to estimate it. It's an indirect way to do it, but for a reason.
Yes, you make reference to a field.
Yes.
So how does it relate to what physicists would call a quantum field?
Yes.
As opposed to, say, a random field, like a Gaussian one-dimensional random field.
Yes. Yeah, that's a very interesting question. My understanding is that I mean, in quantum mechanics, in quantum field theory, usually you are in a regime of like perturbative regime, which means interactions are very weak. So the field there, I mean, for many cases, are roughly Gaussian. So I think people there know how to statistically describe it, which is to use some Taylor expansion with respect to Gaussian field. So here the field, I think it becomes highly like interactive. So
In other words,
yes.
it deals with relativistic mechanics,
Uh-huh.
as opposed to non-relativistic, which would be more classical quantum field analysis.
Right.
But physicists, quantum fields are not just fields, they're a very particular kind of field.
Yeah, there are fields with the property of quantum mechanics. Right.
I have a second question.
Yes.
What about antimatter, which presumably existed in equal quantities early on,
Yes.
and now presumably the antimatter has disappeared? What do you say about it?
It's not related to this, but what my understanding is that we still don't really have a quantitative theory of why they disappear. I mean, yeah, so it, they disappeared by just annihilation with normal matter. That's known. But the question is why the normal matter is more than the amount of antimatter. I think we don't have a good answer for it. We just know that there must be some inequilibrium to make the matter slightly more than antimatter. But yeah, that's a long-standing problem, and I don't think we understand now.
Question,
Yes,
cosmology.
right. Yes.
Hi, this is great, by the way. Can you
Thank you.
characterize for us how much of a win it is to be able to use the scattering transform as opposed to more complicated neural networks? Are we talking about having to use like half as many cosmologists, getting to your lensing map in like half the time? Like, how much of a win is this?
So how much of
How
what?
much of an advantage is it?
I see.
Simple scattering transform as opposed to having to go full neural network.
Yes. Oh, that's a very technical question. That's some type of question I get from cosmology meetings. Uh, so one thing is neural network does require a lot of training set. So one concept we try to advertise like in the community is with the statistic you can get like something like one-shot learning. You see very few number of examples, then you already get the statistical property. But neural networks, because it has too many degree of freedom, so you need to see a lot of examples in order to really get a sense of the distribution. Right. So one thing is we need fewer simulations, and also it runs much faster because this thing is something like just running forward once the neural network. But in neural network, if you need to train, you need to go back and forth several times. Right. So I guess the question will be, what do you gain from using neural networks instead of a simple statistic, if the constraining power is the same? Yes.
What is the structure?
Yes. Yes.
Why is Affiliation, why do you have to go other than
Yeah. Oh, that's a very philosophical question. I mean, very good because I like philosophy. Um, I try to remember, I think more or less is by accident. So by definition, there are two layers of these statistic, like something similar to two layers of neural networks. And in each layer, you have a peak of scale and orientation. So the simplest thing we can imagine is, what about taking like the sum of these and the difference of it? And it's just turned out that when we take the difference of it, we get a visual meaning of curvature. We didn't choose that in advance. We just want to see like what's the meaning of the difference of two statistics. And then it turned out to be these curviness. And we want to see what is the meaning of the average of these statistics. It turned out to be the clumpiness. Yep. Yes.
Very non-technical question. When you showed the, image of the ocean field,
Yes.
The resulting images all showed swirls. Are meteorologists actually using these techniques to predict storms in the rising ocean?
That's good question. I'm not aware of it yet, but that's a good idea. This is kind of recent work. Yeah, so I know actually some astrophysicists changing their interest and going to oceanography nowadays. They are interested in this. yeah, I'm not aware of more application there, but I think that's an interesting idea.
I get the last question. Could you
Yes.
tell a little bit, see how about your experience being a member here at IAS?
Oh, yeah.
Appointment and the opportunity.
Yeah, so oh yeah, I forgot to say that. Thank you so much. It's really by heart. I'm really thankful for all your donations and giving me the opportunity to come here. I mean, IS has been a very prestigious academic place for a long time, and I always wanted to be here, and also feel great when I'm doing science here. So I mean, I don't know other department, but the Astro department is really like free, and we have a lot of discussions and encourage basically people doing different subfields to communicate and to learn from each other. So at least that fit my desire and style. I know some people like to work just on their own thing, but I like to learn more and get like new opportunities and take new opportunities. So I have to like discuss with people. And as Pamela introduced at the beginning, right? I'm searching for Plan 9. I mean, that's not Plan 4 had. It's just because of the like visitors here. There are a lot of visitors coming here and giving talks. And I mean, early this year, there's a visitor coming here doing like search of Plan 9 for many years. And then I realized there's a very deep data set they haven't really searched for. So then why not I do it? And maybe there's opportunity. So yeah, so although it's a very small group here, but like scientists here are really nice. So we're able to really talk with each other and try to understand what each other is saying. Um yeah, and also the housing here is really nice. It's just like probably 1 minute by run and 2 minutes walk. It's too convenient.
Wonderful. Maybe you'll come back and talk about the search for planet.
Oh yes, I really hope so.
Thank you so much.
Thank you.